Yeah, I was wondering. It takes more gas than floor than it does.
All right, so we're talking about the cross product today, but I wanted to do a quick little proof that has to do with the dot product, and this is a proof without words.
Yes.
So this is a very nice little proof. So here I'll do this. I want that to be red. There we go. And we get our some identity for cosine from the dot product. Proving this identity using triangles and unit circle geometry is kind of long and ugly, but this makes it really nice. And if you set up your vectors, you can come up with your other identity, and it's a very easy thing to do. If we did our vectors this way, if this is A and this is B, and that's alpha, and that's beta, and we do the same process to our vectors this way, I would get the difference identity for cosine. So the first time I saw this, I thought it was a really cool, nice little thing. And all this relies on is the law of cosines. The law of cosines is what tells us this that we came up with yesterday. So this proof only relies on the law of cosines. Pretty nifty, huh? Yes.
Aren't you assuming the ends are true though when building cosine off the table to cosine alpha cosine beta minus sin cosine beta?
These are both, it's just both expressions for the dot product. The dot product A dot B is the x components multiplied plus the y components multiplied. So I'm just using the two different representations of the dot product and setting them equal to each other.
Yeah, I see.
Okay. All right. So let's talk about the cross product. Now that we've done this nice little exercise, the cross product, another kind of vector multiplication. We call it the cross product. It's also called the vector product. So remember that the dot product is always a scalar. Cross product gives us a vector. So if we have u, our vector u is u1i plus u2j plus u3k, and vector v is v1i plus v2j plus v3. Okay, we're going to define our cross product, u cross v, as, and we have a long expression here, u2 v3 minus u3 v2 I minus u1 v3 minus u3 v1 j plus u1 v2 minus u2 v1. Okay. And our cross product is only defined for three-dimensional vectors. We don't have a definition of a vector in 2 dimensions. One important thing that makes the cross product very useful is u cross v is orthogonal to u and v. And the direction of the cross product, if we're in a right-handed coordinate system, so we use the right-hand rule. And the way I think of it as, if my fingers point in the direction of u, and v is in the direction of my palm, if I cross u onto v, my thumb points in the direction that the cross product goes. So I'm crossing u. I think of the cross product as a kind of an action thing. So I cross u onto v, and my thumb points in the direction of u cross v. So we use the right-hand rule. An easy way to calculate this expression is kind of messy. An easy way to calculate this, to remember how to calculate it, is with a determinant form. So I say u cross v is this determinant ijk u1, u2, u3, v1, v2, v3. So this is not actually a determinant. It's just the form of the cross product takes the same form as the determinant of a matrix. Is everybody familiar with how to calculate determinants? Methods of calculating determinants? Kind of. The one that I think is most common is, I would say, this is I times, and I'm going to what I do is I cross this row and this column out and multiply these two together. So if I'm going to draw a dashed line in here. So if I do this for the I, that in red, and I don't want an arrow. So I would cross this row and this column out and find the determinant of this 2 by 2 matrix. So this would be I times U2 times V3. And then when I go right to left, my sign is negative, U3 V2. So I cross the row and the column out that I'm looking for and then find the determinant of this 2 by 2 matrix. And then for the J component, for the second one, I always use a minus sign, minus J. And for that part, and I'm going to cross out the J row and column. So I would do this like so. And then I would take the determinant of these, the two that are not crossed out in blue. So U1 V3 minus U3 V1.
Isn't there like a little jingle thing to remember going down and left or something? In the when you have a 2 by 2 matrix left.
I never learned a jingle.
Like rhymes a little bit so you can remember you go like down, like diagonal.
Obviously it didn't work very
well. Another way that you can think of this that can be helpful is if you don't remember this 2 by 2, the 2 by 2 and crossing out the rows and the columns, I'll write it another way. So if we say U cross V equals this determinant, U1, U2, V3, V1, V2, V3. If you append the first two columns on the left side of your, or I'm sorry, on the right side of your determinant, so I'm going to append this I'll do that in red. Let me undo that. So I'll do I, U1, V1, and I'll do the next column in blue, J, U2, V2. You can also do it this way. And I'm multiplying the numbers along this diagonal, along each diagonal. So I would get, when I did it with this method, I would get I times U2 V3 plus J times U3 V1 plus K times U1 V2. And then I do minus and I go along the opposite diagonals. So I go this way. And on the diagonals that go from right to left, I do minus. So I would get minus K times U2 V1 minus I times U3 V2 minus J times U1 V3. And then I can combine these and get my determinant. So those are two ways you can think about doing this determinant with the cross product. So either way works. The first way you get everything combined together more quickly. And I have had some students that just memorize that first form. And they just write the cross product out that way from that very first form. So any of these ways will work for finding the cross product. So questions about what the cross product is and methods of calculation. So this next part is kind of dry and not. It's just a lot of properties. I want to list out the properties of the cross product. The cross product behaves a little differently than the dot product. So I just want to list out those properties. And we'll use these properties throughout the rest of the year to come up with some other conclusions when we're working with vectors. So we have a bunch of properties. U cross V is negative V cross U. So if I change the order, I change the sign. We can do the associative property, U cross V cross W. Or not, I'm sorry, not the associative property, the distributive property holds, is U cross V plus U cross W. We have scalar multiplication, RC times U cross V. It's just, the scalar can be multiplied by either of the vectors, CU cross V, and that equals U cross CV. U cross the 0 vector equals the 0 vector cross U, and that equals the 0 vector. And this is not a 0 scalar, this is the 0 vector. Question?
For the distributive property, it's not the distributive property unless that's plus. From the associative property.
Oh.
Except not the associative property.
Yeah, no, this.
In the book, it's U cross V plus W plus U cross.
Yeah, that's
For this one, U cross V plus U cross W.
And that one in the book is written, the original one should be U cross V plus W.
Oh, V plus W. I wrote a cross instead of a plus. Yes, that's how it is in my notes also. So I wrote a cross instead of a plus. Thank you. All right, so this is the 0 vector. Remember, the 0 vector is not a scalar. And here we have C is a scalar. U cross U, any vector crossed onto itself is the 0 vector. And finally, U dot V cross W is U cross V dot W. And this is called the scalar triple product or the box product. So those are our properties there are algebraic properties, our geometric properties. So what our cross product is telling us about the vector geometrically. If theta is the angle between the vectors, then We already said our first property, 1, U cross V is orthogonal to U and V. The magnitude of U cross V is the magnitude of U times the magnitude of V times the sine of the angle between them. And we can do a similar, the proof that we did right at the beginning, we could do a similar proof for the sum and difference formula for the sine of the angle using our definitions of the cross product. We could come up with our sum and difference formula for sine of the angle. Let's see. Our third one, U cross V, is the zero vector if and only if U and V are parallel. And remember, parallel means that one is a scalar multiple of the other. So the cross product gives us the zero vector if and only if they're parallel. Our fourth geometric property, the magnitude of U cross V is the area of the parallelogram with U and V as adjacent sides. The vector U and vector V as adjacent sides. And our box product, the reason we call it the box product, is U dot V cross W is the volume of the parallelepiped or the box, the parallelepiped with U, V, and W as adjacent sides. So that's why they call it the box product. It gives us the volume of that box with these three vectors as adjacent sides. Most of the properties are very familiar. The ones that we have to be careful with, if we take the cross product in the opposite order, are sign changes. And if our cross product is 0, that tells us our vectors are parallel. And what else? I think those were the main ones. That the sign changes if we change the order, and that our cross product 0 if the vectors are parallel. Questions on our property? The box product, we really are not going to do much with the box product. I just wanted you to have seen it and to at least have some introduction to it. All right, let's do a couple of calculations and then we're done. So we want to find, we're just going to calculate a cross product. Find A cross B. Where A is 2I plus J plus K, and B is negative 4I plus 3J plus K. So I'm going to use the determinant form. This is, I'll say A cross B is IJK 211 negative 431. And this is going to be I times 1 minus 3 minus J times 2 plus 4. Let's see, minus J times 2 plus 4 plus K, crossing these two out, 6 plus 4. So I get minus 2I minus 6J plus 10K. Did I do that right? Yeah. Yep, that's right. So there's our cross product. I just used the determinant form and found our cross product. Questions on how we calculated that? You can use any of the forms that make sense to you to calculate the cross product. I just find it quicker and easier to use the crossing out and looking at the 2x2 determinant.
And it's like covering up one line.
Covering up one line, right.
That's basically the same concept.
Right. The important thing to remember here is that this sign is negative. For the J component, we give negative 4. Yeah. Well, one, that comes from the rules of finding the determinant of a matrix. Is, what's that? Right. And I think, if I remember correctly, it's the alternate rows. They alternate positive and negative when we calculate it. So if you're calculating a larger determinant, the signs alternate.
So if we were doing fourth dimensional vectors.
Right. And when we do the 2x2 determinant, this first one is positive, the first diagonal is positive, the second diagonal is negative. So they alternate that way. So for my second example, the other type of calculation you might see, just asking a question in a different form, we want to find a unit vector orthogonal to both A equals I plus 2J minus K and B equals minus 2I plus 2J plus 2K. So this is basically asking the same question in a different form. It asks for a vector orthogonal to both of these. We know that the cross product is orthogonal to both vectors that form the cross product. So this is just another way of asking to find the cross product. This type of problem will show up in lots of contexts as we move forward. We're going to be interested in finding a unit vector that's orthogonal to a plane, to a surface. And we have some other vectors that define parts of that plane or surface. Yes?
So for this one, are there two answers? You can go A cross B.
Yes. Right. So we, I was going to get to that. So if we form the cross, we can form the cross product in either order. I could do A cross B or B cross A, and what that would give me was a vector, the orthogonal vector in one direction. If we did the opposite, we would get the negative sign, and it would be still orthogonal to both vectors. It would just point in 180 degrees the opposite direction. So you can think of it as pointing up or pointing down. It's still a unit vector orthogonal to both, just in opposite directions. So we'll carry through, calculate our cross product here. A cross B is orthogonal to both. So I'll just do A cross B, and we'll do my determinant form. So I get 1, 2, negative 1, and negative 2, 2, 2. If you're given a two-dimensional vector, and we want to form, if we have a three-dimensional vector and a two-dimensional vector, or two two-dimensional vectors, we just enter a 0 for the k component, which is 0k, so we'd have zeros here. And that's how we would form our cross product. So this is going to give me I times 4 plus 2 minus j times 2 minus 2 plus k times 1 plus 2. So I get, did I miss my k? Yes, I do 4. Negative, let's see, 2. What did I do? I crossed out my k. 2, there we go, plus 4. There we go. And that kind of mistake, I make that kind of mistake when I do cross products. Not often, but what I have today. But it's an easy mistake to make, going quickly and missing your determinants. So anyway, we get 6i plus 6k. And the magnitude, we wanted a unit vector. The magnitude of A cross B is square root 2 times the square 2 times 36, which is 6 square root 2. So our unit vector is square root of 2 over 2 I plus square root of 2 over 2 k. So I'm dividing each of these by 6 square root 2. So that would be my unit vector. If I found the vector in the opposite direction, I would just have minus signs here if I did B cross A. Everybody good with calculating cross products? Okay. Homework, page 796. There you go.
Mr.